Hello. My topic today is the continuous wave lidar method, or as you also could call it, line-of-sight sodium profiles during laser guide star adaptive optics operation. So this method yields sodium profile from the LGS. The overall scope of this work is to see if the need for the NGS focus sensing can be removed by laser guide star adaptive optics. Two different applications could be thought of. So since the method yields line-of-sight sodium density profiles, it could also allow for acquiring data on the sodium density structure during telescope operations from the LGS. And it could also be used, the profiles could be used for matching filter algorithms as an input. I will not talk too much today on matching filter algorithms because I'm not an expert in it. So let me remind you on some of the sodium layer properties. So the sodium layer is in the mesosphere at about 80 to 110 kilometers of altitude. The sodium originates from ablation from meteorites, and at the lower edge, the sodium leaves the layer by chemical reactions. The centroid is somewhere around 90 kilometers typically, and the layer shows temporal and spatial evolution. The structure of the layer is affected by Kelvin-Helmholtz instabilities, gravity waves, and the formation of sporadic sodium layers, and also by meteor trails running through the line of sight. Here we can see examples of the sodium layer evolution. So this is data taken at the LZT in Canada. This is the evolution of about 4 or 5 hours. And here you can see gravity waves with a period of about 4 minutes, or a few minutes. So the problem with the variability in the sodium layer is that the centroid is moving. And so laser guide stars adaptive optics systems cannot distinguish between changes in the sodium layer centroid and changes in the atmospheric focus. So changes in the sodium centroid will induce a focus wavefront error, which can be calculated by this formula. So the wavefront error is dependent on the square of the telescope diameter divided by the altitude of the centroid and times the offset. Sorry, the altitude goes in by being squared. So this d square in the formula is also the reason why for common, or at the moment for state-of-the-art telescopes with diameters of 10 meters, the effect isn't as strong as it will be for extremely large telescopes. So here for comparison, there's a pupil with a 10-meter diameter, and then the pupil of the ELT, and you can see the offset, the phase offset, for the defocused wave increases to the edge of the aperture. Just to give you a number, so for the ELT, 1 meter of centroid change will result in a wavefront error of 7 nanometers. The method. So the method works by a partial amplitude modulation of a continuous wave laser. So the amplitude is modulated by a device like an acousto-optical modulator. We have tested, and it has been shown that an acousto-optical modulator can modulate the amplitude on a megahertz scale. So the modulation is done by a modulating sequence, which needs to have a special property its autocorrelation needs to be delta-like, so it needs to be like a delta function. Then the received fluorescence from the sodium layer, the signal from it, can be cross-correlated, and a profile can be retrieved from the signal after the cross-correlation. Yeah, the laser is. Yeah, the actual. So it's a bit misleading. So it's a. Yeah, so it's partially amplitude modulated. Of course, in an adaptive optic setup for an ELT, one wouldn't block the light going to the wavefront sensor. So the idea for this method is to use some light which is leaking out of the system somewhere. So we assume that either some light leaking from mirrors or from the beam splitter could be used by using a notch filter for 589 nanometers and having a photomultiplier on the back of the notch filter. And we assume that something like 3% of leakage light could be used, but of course this could be increased or decreased. Yeah. So we ran a study on how feasible this method is on extremely large telescopes. So what we did is we did an analytical calculation and ran some numerical simulations at the same time. And for the error, the analytical calculation comes up with this formula. So the error in centroid is given by this formula, which depends on the modulation strength. And N0 is the total number of photons at 0 modulation, the number of samples, and the altitude range of the layer. So it has to be said that once you modulate your laser, of course you're sacrificing some flux. So the average laser guide star return flux will be lower than when there is no modulation. This image, or this figure, shows results from the simulations. So into the simulation, a truth profile went in as input parameter. And then you can see this dashed line is the retrieved profile, where there was noise added. So we always look at the photon noise limited case. And without noise, we retrieve the exact profile, which also should be the case. So now we compare this formula to the results of the simulation. So we did these simulations for different profile shapes, for the different ELTs, and for different integration times. And you can see the comparison of the simulations and the predicted error from the analytical method or analytical calculation here. So the dots represent results from the simulation. So the different colors are different integration times, and the dashed line is the predicted error by the analytical calculation. And you can see that the simulation and the analytical calculation agree well. As parameters, we used a laser guide star of 7th magnitude. A telescope throughput of 30% was assumed, and 3% of leakage line. And this is a result for the ELT. So now once you have the centroid error, of course you want to know what the corresponding wavefront error is. So this can be done with a formula which I showed you in the beginning. And this way you can transfer the centroid error into a wavefront error, which can be seen here. So on the y-axis we have the wavefront error, and on the x-axis the modulation strength. And you can see the results for the different ELTs for different integration times, so the different line colorings or line styles are the different integration times. And one, yes? Oh, okay, sorry, yeah. Great, thank you. One can see, so the results are also dependent on air mass. So this are the results for Zenit. But Zenit actually is the worst case, so it improves slightly with for lower altitudes. And one can see that if one used 1 LGS for 60% modulation, one could retrieve 50 nanometers wavefront error on all ELTs for 5 seconds integration. Since the ELTs will have multiple laser guide stars, you could not only think of using 1 laser guide star for retrieving the profile, but all 6, for example. So these are the results for when you use 6 laser guide stars. And so here for reaching that 50 nanometers wavefront error, you only need 30% of modulation. Yes?
Does that assume each of the laser guide stars have the same profile?
Yes, so there have been studies. The results haven't been published yet for the horizontal structure function of the sodium layer, and it shows that you can assume the same profile on all laser guide stars. Thomas might know better because the.
I heard the first one, the second one.
6 lasers at 40 meter distance. Pretty stable to 1 meter of barycenter. Pretty stable to 1 meter of barycenter, remember.
Oh, well, this is...
Yeah, because if you are doing all this to get the 7 nanometer.
Yeah, and just to remind you, so 30% of modulation means 15% of reduction in laser guide star return flux. So to see the capabilities of this method, these plots actually are even better suited. So here we have the number of photons on the y-axis, the modulation strength on the x-axis, and the wavefront error are the contours. The corresponding wavefront error are the contours. And this is for the 3 different ELTs. And then there is a normalization constant for the number of photons, gamma 0. So gamma 0 is the number of photons for 0 modulation at an integration time of 1 second, a flux at the primary mirror, which corresponds to a 7th magnitude laser guide star, and again, a telescope throughput of 30% and a fraction of leakage light of 3%. And a used laser, so the number of laser guide stars used is just 1. So this means if you use these parameters for n0, the fraction will be just 1. So you're down here at this dashed line. But now if you, for example, used 6 laser guide stars, of course the fraction of n0 over gamma 0, since you would use 6 laser guide stars, would be multiplied, or would be 6, so you would move up here. And now you can go on thinking of, for example, in the future, having a higher return flux from a more powerful laser, or integrating, or let's say we integrate for 2 seconds and have double the return flux with using 6 laser guide stars, and then you end up with a factor of 6 times 2 times 2, which is 24. So then you're at the upper edge. And this shows that in this scenario, which might be a future scenario, you could use 60% of modulation to be below 20% of wavefront error. Sorry, not 20%, 20 nanometers. So the conclusions, retrieving profiles, I forgot something here. But what these plots also show is that if you want to use one laser guide star and want to use just fractions of seconds, it might be difficult to achieve high accuracy, since you would try to get in this region down here, and if you look at the contours, the wavefront error is quite high in that region. So generally, for these low fractions of n0 over gamma naught down here, the contours run horizontal. So this means you really need to do something which increases your number of photons. While in this upper part, the contours run vertically, which means that a gain is achieved by changing your modulation strength, increasing your modulation strength. Okay, so the conclusions. Retrieving profiles inducing wavefront errors below 50 nanometers on timescales of some seconds is possible for ELTs. We've seen different scenarios, so one could use 1 LGS and 60% of modulation. Also, one could use in a multiple laser guide star system, one could use 6 LGS and 30% of modulation. Maybe in the future, so more return flux is available. Maybe so there are activities ongoing like chirping and also developing higher powered lasers. So in the future, maybe a wavefront error below 20 nanometers is possible with using 6 laser guide stars and 2 seconds integration time. But also the profiles could be used for matched filters. Here, a more quantitative study needs to be done. And the retrieving of high accuracy profiles at the moment seems difficult on very short timescales. But at the moment, it's not clear what the timescale really is for, or what the needed timescale is. So there needs to be more work done in this regard. Yeah, thank you for your attention.